Pluto is a remote and perplexing, more modest planet that was once a piece of our sun-fueled system's planetary gathering. However, later surprising announcements by conspicuous astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding discovery. They suggested that this cool world is on a potential collision course with Neptune. Yet how could this work out, and what may be the repercussions of such a giant event? Are we seeing a fascinating cosmic peculiarity, or is there something else to this coming limitless struggle? Join us as we investigate the possible results of a Pluto-Neptune impact. Pluto, a previous planet that was renamed as a dwarf planet in part due to its astonishing orbit, remains a subject of interest and investigation in the cosmic community. According to recent figures by leading scientists, Pluto's orbit is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a likely dangerous collision between these two planets that could present a critical risk to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our nearby planetary gathering. It requires an amazing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't, without a doubt, finished one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its exceptionally elliptical shape, wandering astoundingly from the almost round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, determined at 17 degrees to the ecliptic plane. The manner in which Pluto follows is significantly more extreme compared to other planets. This inclination and elongated nature add layers of complexity to its orbital design. One of the most intriguing aspects of Pluto's orbit is its intersection point with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we might expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The examination of Pluto's orbit began not long after its discovery. Initially, astronomers attempted to understand its unusual path. In contrast to planets whose orbits lie somewhat near the ecliptic plane, Pluto's orbit stood apart with its steep inclination and stretched shape. The mystery deepened with the confirmation that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricate design of space mechanics. The three-body problem in space involves figuring out how three objects like Pluto, Neptune, and the Sun move and affect each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how the orbits of Neptune and the Sun's gravity all interact in a complicated way. The terms libration and resonance libration, along with the VSK oscillation, are part of this puzzle, as indicated by astrophysicists. What's keeping all planets in their orbits is a U-libration. In the specific context of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it's arranged at least 90 degrees away from Neptune. This spatial division is critical in keeping their orbits from colliding. Resonance libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated entirely above their orbital plane, providing an additional layer of protection from potential impacts. Another significant part of this condition is the VSK oscillation, named after three researchers, von Zippel, Kappas, and LV, who studied how objects move in space. It describes how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VSK oscillation helps us understand why its orbit around the Sun is so unusual. Despite its seemingly turbulent path, Pluto's orbit remains stable for an extraordinarily long time, like billions of years. This means Pluto's venture around the Sun has a kind of order to it, even if it seems unpredictable at first. Predicting limitless events, especially when they involve violent orbits like Pluto's, presents critical challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a powerful means to understand and predict the future path of celestial bodies, they also highlight the limitations of our predictive abilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or deviation can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the turbulent nature of celestial orbits like Pluto reminds us of the constantly evolving and dynamic nature of the universe. While we have made significant steps in understanding space, the case of Pluto serves as a reminder that our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can create far-reaching effects on the stability and behavior of various bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential impact between Pluto and Neptune? Despite all these intricate forces trying to prevent such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers an interesting perspective on the mysteries of our nearby planetary system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's interest in the unexplored realms of space. Tyson's position on Pluto's renaming is grounded in the ever-growing knowledge of our solar system. He sees the renaming not as a demotion, but rather as a significant adjustment in alignment with our developing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and transformation. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these questions, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planetary system. His work stresses that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another respected physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often tumultuous forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with visionary concepts, making him an important voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to predict and understand potential astronomical events. He sees the interactions between celestial bodies as an important area of study, not just for academic interest but for practical implications. The potential collision between Pluto and Neptune, for instance, isn't just a theoretical situation, but a reflection of the dynamic and often violent nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His perspective highlights the significance of being prepared for the unexpected in space. Kaku suggests that the more we understand the forces at play, the better prepared we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's viewpoints converge on the idea that space is a domain of boundless discovery and that our current understanding, while significant, is still limited. Their emphasis on the need for ongoing exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now, but also anticipating how they may change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for effective scientific inquiry, advanced technology, and a willingness to revise our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational forces acting upon them. Therefore, a direct impact between Pluto and Neptune is extremely unlikely. However, the complexities and potential perturbations in orbital dynamics still mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may pose. While the possibility of a Pluto-Neptune collision is largely theoretical and considered unlikely with current understanding, it highlights the importance of continuous research and observation in space science. Advances in technology, including more advanced telescopes and virtual simulations, will help astronomers refine their models and predictions, ensuring that we stay abreast of the dynamic and ever-changing nature of our nearby planetary system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for ongoing investigation and a flexible understanding of our universe. The potential impact scenario, while highlighting the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast yet still unclear domains in our understanding of space. Through continued research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe. Pluto continues to captivate scientists and space enthusiasts alike with its distant, mysterious nature. While its status as a dwarf planet has long been debated, its orbit and peculiarities remain at the forefront of astronomical curiosity. The warning voiced by Neil deGrasse Tyson and Michio Kaku about the potential for an impact, while speculative, serves as a reminder that there is still much to learn about our solar system. The incredible forces at play within our solar system, combined with the endless possibilities of future discoveries, continue to fuel both scientific exploration and public imagination about the cosmos. In a sense, we are all passengers on the ever-changing journey through space, curious, uncertain, and constantly striving to understand the unknown. The topic of Pluto and its potential interaction with Neptune touches on a larger theme in astronomy: the unpredictable and dynamic nature of the cosmos. While we have made significant strides in understanding the forces that shape the orbits of planets and other celestial bodies, there remain many unknowns, especially when it comes to the long-term stability of the solar system. The gravitational influences between planets are not static. They can shift over time, potentially altering orbits in ways that are difficult to predict. This uncertainty drives the need for constant observation and reevaluation of our models, which is where advancements in technology and computational modeling become crucial. In addition to the gravitational relationships between Pluto, Neptune, and other planets, one of the fascinating aspects of space research is the discovery of how smaller objects, such as asteroids and comets, can also influence the orbits of the larger bodies. These objects, while seemingly insignificant in comparison to the size of planets like Neptune, can cause slight perturbations in the orbits of nearby planets. Over long periods of time, these small forces can accumulate and lead to changes in the trajectory of a planet's orbit. This phenomenon, known as gravitational perturbation, highlights the intricacy of the solar system's dynamics and underscores the potential for unexpected changes in orbital patterns. Astrophysicists are also delving deeper into the concept of cosmic resonance, which occurs when celestial bodies exert regular, periodic forces on each other. As mentioned earlier, Pluto and Neptune are in a form of orbital resonance where their orbits are linked in a way that prevents them from colliding. This resonance helps maintain the relative stability of their orbits over long periods, but this stability is not absolute. There are forces at play that could potentially disrupt these resonances over time. For instance, interactions with other bodies in the solar system, such as passing stars or massive interstellar objects, could disturb the balance that has kept Pluto and Neptune's orbits in sync. While the likelihood of such an event occurring in the near future is low, the potential for cosmic events to alter orbits is an ongoing subject of study. Another factor that could influence Pluto's orbit is the presence of the Kuiper Belt, a region beyond Neptune that contains a vast number of small icy bodies, including dwarf planets, asteroids, and comets. The gravitational influence of these objects can have subtle but significant effects on the orbits of objects like Pluto. In fact, many of the discoveries regarding Pluto's orbit have come from studying how the Kuiper Belt objects interact with the planet. Some researchers believe that the gravitational interactions between Pluto and other Kuiper Belt objects could explain the eccentricities in its orbit, adding another layer of complexity to our understanding of its movement through space. Looking even further into the future, some astronomers have raised the possibility that Pluto could be ejected from the solar system entirely. While this scenario is extremely unlikely in the short term, it's not beyond the realm of possibility in the distant future. As the sun evolves, it will eventually go through phases that could alter the gravitational landscape of the entire solar system. The sun's transition into a red giant will significantly affect the orbits of all the planets, and in some models, this could lead to the ejection of objects like Pluto from the solar system. However, this is a process that would take billions of years to unfold, and many factors could influence the outcome. The study of Pluto's orbit not only helps us understand this distant dwarf planet, but it also offers important insights into the behavior of other small objects in the solar system. The more we learn about the mechanisms that govern the motion of these bodies, the better we will be able to predict the future dynamics of the solar system. With the help of more advanced technology, including next-generation space telescopes and deep space probes, scientists are gaining a clearer picture of how objects like Pluto move in relation to the Sun and other planets. Furthermore, the possibility of a collision between Pluto and Neptune, though unlikely, serves as a reminder of the unpredictable nature of space. Despite our best efforts to model the solar system, the true complexity of celestial mechanics is far beyond our current understanding. As technology continues to improve, we may one day uncover new forces at play in the solar system, reshaping our perceptions of what is possible.